There are moments in climate science when the models stop disagreeing, when every major forecasting system, European, American, Australian, Japanese, points in the same direction at roughly the same intensity, and the scientists running them begin using words they normally keep in reserve. Unprecedented, off the historical chart. Potentially the strongest event of the modern era. We are in one of those moments right now. As of early July 2026, the 2026 El Niño is no longer a question of weather. It is confirmed. WMO Secretary General Celeste Saulo stated directly, El Niño conditions are already underway and are forecast to strengthen rapidly into a strong event. The atmosphere has already begun to respond. Thunderstorm activity is increasing over the central and eastern Pacific and is suppressed over Indonesia. The classic signature of an El Niño reorganizing the world's tropical weather patterns. Trade winds have weakened. The warm water that was being pushed westward has stopped being pushed, and it is pooling across the central and eastern Pacific in quantities that multiple independent forecasting bodies are now describing as consistent with something the instrumental record hasn't seen before. The question that scientists are now watching, intently, carefully, with the kind of attention that professionals in this field reserve for genuinely unusual situations, is not whether this El Niño will be significant. It will be. The question is whether it will become the strongest El Niño in recorded history. And the most current data, as of the week you're watching this, is making that outcome look increasingly probable. To understand why that matters, and why this particular event is being tracked with an urgency that hasn't been present in previous El Niño cycles, you need to understand what El Niño actually is at a physical level, what super means when scientists apply that label to it, and what the specific signals being watched right now are telling forecasters about where this is heading. El Niño is a phase of a naturally occurring climate oscillation called the El Niño Southern Oscillation, or ENSO. In a normal year, trade winds blow consistently westward along the equatorial Pacific, pushing warm surface water toward Australia and Asia, and allowing cooler water to upwell along the coast of South America. This keeps the eastern Pacific relatively cool, the western Pacific relatively warm, and rainfall and atmospheric circulation distributed in a pattern that billions of people's agricultural systems, water, infrastructure, and seasonal weather expectations are built around. El Niño happens when that system breaks down. THE trade winds weaken, sometimes reverse. The warm water stops being pushed west and sloshes back east across the entire Pacific Basin, and sea surface temperatures in the GEOSO, central and eastern equatorial Pacific climb, significantly above their long-term averages. When that warm water vents heat into the atmosphere above it, it reorganizes atmospheric circulation globally, shifting the jet stream, redirecting storm tracks, redistributing rainfall patterns, and raising global average temperatures above the underlying trend for months to years afterward. The World Meteorological Organization classifies El Niño events by the magnitude of the sea surface temperature anomaly in a monitoring region called Niño 3.4, a patch of ocean straddling the equator in the central Pacific. Warming of 0.5 degrees Celsius, above average for a sustained period, constitutes El Niño conditions. 1 degree is moderate, 1.5 degrees is strong, 2 degrees or more is what many scientists informally call super, a rare historically consequential category. There have been only 5 super El Niños since 1950, the last occurring 11 years ago in 2015 to 2016. They also occurred in 1997 to 1998, 1991 to 1992, 1982 to 1983, and 1972 to 1973. Super El Niños have also been documented in 1888 to 1889 and 1877 to 1878. NOAA's climate prediction center is highlighting a 63% chance of a super El Niño this winter, between the 3-month period of November 2026 through January 2027. And as of its most recent July update, NOAA states there is an 81% chance of a very strong El Niño during October through December that would rank among the largest El Niño events in the historical record, going back to 1950. NOAA's own Geophysical Fluid Dynamics Laboratory ran its forecasting model 30 times in its July update, and every single one of the 30 runs projected a peak El Niño strength that the laboratory described as looking competitive with the strongest events observed over the past century. Every single run. The ECMWF, the European Center for Medium-Range Weather Forecasts, widely regarded as the world's most capable operational forecasting system, has been revising its El Niño projections consistently and in only one direction. New ensemble model runs from ECMWF, NOAA, and Australia's Bureau of Meteorology now align on a high-impact trajectory, with several forecasts suggesting this event could become the strongest El Niño in modern history, potentially surpassing the record-breaking event of 1877 to 1878. The early July ECMWF projections showed its median ensemble run targeting sea surface temperature anomalies in the Niño 3.4 region of approximately 3 degrees Celsius above. The average by autumn, with some individual ensemble members, the high-end scenarios, pushing toward 4 to 4.5 degrees. Values at that upper range, if verified, would be genuinely unprecedented in the observational record. The latest forecasts are also continuing a trend of showing a stronger El Niño with each new forecast run, as they adjust to the latest atmospheric development rivaling the strongest events of the past. The physical engine behind this extraordinary intensification trajectory is a massive subsurface Kelvin wave. A Kelvin wave is a below the ocean surface eastward across the Pacific, not visible at the surface, but detectable by the network of Argo buoys, moored sensors, and satellites that monitor subsurface ocean temperature and the sea level height anomalies that warm, expanding water produces. A rare triplet of tropical cyclones in the western Pacific earlier this spring produced strong, persistent westerly winds that reversed the normal trade wind direction. These bursts mechanically pushed warm surface water eastward and acted as a known precursor to large El Niño events, the April triplet. Cyclones Mila and Vayanu in the southern hemisphere and Super Typhoon Sinlaku in the northern hemisphere, forming a near simultaneous alignment, generated the kind of sustained westerly wind burst that oceanographers associate with the initiation of the largest ENSO events. Climate scientist Daniel Swain flagged the pattern in early April, noting it strongly reinforced the eastward Kelvin wave. This subsurface heat pulse is expected to rise to surface levels, acting as a release valve that will kickstart the reorganization of global weather patterns starting in the tropics. The comparison that keeps appearing in the scientific literature and in the communications of the agencies monitoring this event is to 1877 to 1878. Not 2015 to 2016, not 1997 to 1998, but the pre-instrumental era event that climate historians have reconstructed from proxy records and contemporary observations, estimated to be the strongest El Niño in several centuries, and associated with catastrophic simultaneous droughts and famines across 3 continents. Some individual ensemble members exceed plus 4 degrees Celsius, values that would be off the historical chart. The comparison is not being made casually. It is being made because the current trajectory of the subsurface heat reservoir and the strength of the atmospheric coupling that has already begun, the reorganization of tropical convection, the weakening of trade winds, the warming off South America, is tracking ahead of both 1997 and 2015 at the same stage of those events' development. Zeke Hausfather, a climate scientist closely following El Niño model projections, said the consensus is definitely shifting towards an even stronger event. The model runs have been consistently showing higher probabilities for a very strong event compared to a few months ago, and every month sees higher estimates, he said. Currently, the odds of seeing a record-strong El Niño event this year are quite large. Michael Tippett, an atmospheric scientist at Columbia University, told CNN that model projections are now approaching unprecedented levels, saying, "I think it's fair to say that, depending on the model, the forecasts are close to unprecedented." The WMO said the most rapid strengthening is likely during July through September, with impacts expanding globally through the northern hemisphere in the autumn. According to NOAA and GFDL forecasts, the event may peak between November 2026 and January 2027 before gradually weakening later in the winter and spring. What happens globally when a super El Niño peaks is not uniform, and this is a crucial distinction that the scientific community is careful to emphasize. El Niño doesn't affect every region in the same way, and even strong events can produce different regional outcomes than the historical average. The 1997 to 1998 event produced catastrophic rainfall in California. The 2015 to 2016 event, comparable in Pacific anomaly strength, largely missed it. Same classification, different regional fingerprint, because El Niño is one influence among many operating on global weather simultaneously. What the forecasting agencies are careful to say is that a stronger El Niño makes characteristic impacts more likely, not certain. With that caveat in place, the picture for different regions of the world is becoming clearer as model agreement tightens. Index 44.1. The July through September 2026 rainfall outlook reflects a pattern consistent with a strengthening El Niño event. Enhanced likelihood of above normal rainfall is forecast across the central and eastern equatorial Pacific, while below normal rainfall is more likely across parts of the tropical Indian Ocean, the Indian subcontinent, and much of Australia. Across equatorial Africa, forecasts show a prominent east-west contrast. Land areas bordering the northern Gulf of Guinea are forecast to receive above normal rainfall, in contrast to below normal rainfall for the greater Horn of Africa. Below normal rainfall is also forecast for parts of Central America, the Caribbean, and northwestern South America. Wetter than average conditions are more likely across portions of the southwestern United States. For Europe specifically, forecasts suggest a north-south contrast, with increased chances of above normal rainfall in southern Europe and below normal rainfall in northern Europe through the July to September period. But for the UK and northern Europe, the more consequential El Niño signal tends to arrive not in summer, but in the autumn and winter that follow, specifically through its influence on the North Atlantic Oscillation and the winter jet stream position, which determines whether the UK gets a mild, wet Atlantic winter or a cold, blocked one. Historical El Niño winters have been associated with both, depending on which phase of the atmospheric response dominates, making precise UK winter forecasting for 2026 to 2027 genuinely uncertain, even as the Pacific signal itself becomes clearer. WMO scientist Alvaro Silva was direct about the temperature dimension. El Niño will also give an extra boost to global temperatures. We know that during El Niño years, the global temperatures normally reach record levels. This connection between El Niño strength and global temperature anomaly is one of the science. The 1997 to 1998 Super El Niño made 1998 the warmest year on record at the time. The 2015 to 2016 event made 2016 the warmest year on record by a substantial margin. Given last year was the planet's third warmest year, it seems like a near certainty that new heat records will be set in 2026, possibly again in 2027. The Met Office's own WMO annual forecast report put a specific number on this, an 86% probability that at least 1 year in the 2026 to 2030 period will be the warmest year on record globally. The El Niño, now developing, substantially raises the probability that 2027 specifically will be that year. The compounding factor that makes this particular event more alarming than previous super El Niños is what climate scientists call the baseline. Every El Niño adds its anomaly on top of whatever the underlying global temperature is. In 1997, it added its warming pulse to a planet that had not yet experienced this, had the cumulative warming of the last 3 decades. In 2015, it added its pulse to a warmer baseline. In 2026, it adds its pulse to the warmest baseline in recorded history. A global ocean running at temperature anomalies that would themselves have been considered extreme in any previous decade, before the first Kelvin wave of this year's event has even fully surfaced. As Friederike Otto, professor in climate science at Imperial College London, put it, El Niño itself is not the reason to freak out, but rather the fact that it is now happening on an increasingly warmer baseline. Scientists relied on something called plasma oscillation events, brief bursts of activity triggered when shock waves from solar flares, originating back near our own sun, eventually rippled outward and slammed into the surrounding interstellar plasma, months or even years later. When that happened, Voyager's instruments would pick up a brief, musical-sounding whistle, and researchers could calculate the plasma's density based on the pitch and characteristics of that signal. When that happened, Voyager's instruments would pick up a brief, musical-sounding whistle, and researchers could calculate the plasma's density based on the pitch and characteristics of that signal. The very first time this happened, back in November of 2012, just months after Voyager 1 had crossed into interstellar space, scientists got their first ever confirmed audio evidence that the spacecraft had truly left the heliosphere behind. Then, 6 months later, a second whistle arrived, this time noticeably louder and higher pitched than the first. Even from those 2 early data points alone, it was already becoming clear that whatever region Voyager 1 was now traveling through, it appeared to be getting thicker, and doing so surprisingly quickly. The problem was, these events were rare, happening only about once a year, which left huge, frustrating gaps in the data. Then, in 2017, something changed. Voyager 1's instruments began detecting a completely different kind of signal, a faint narrowband hum that wasn't tied to any solar event at all. Unlike the sudden, dramatic whistles triggered by solar shock waves, this new signal was quiet, persistent, and continuous, almost like discovering a constant background frequency nobody knew was playing the entire time. Stella Ocker, a researcher at Cornell University who led the study analyzing this discovery, described it as offering a genuinely new way to measure the density of interstellar space, opening up an entirely new path for studying the structure of the region immediately surrounding our solar system. This was a big deal for one simple reason. It meant scientists no longer had to wait around for rare solar shock waves to get a snapshot of the plasma density. Voyager 1 was now essentially humming a continuous, steady note that researchers could track in real time, regardless of what the sun happened to be doing at any given moment. Shami Chatterjee, a research scientist at Cornell, involved in the work, explained it simply. He said that regardless of what the sun is doing, Voyager keeps sending back detail, essentially reporting back the exact density it's currently moving through, over and over, continuously, as it drifts farther into the dark, So what's actually causing this unexpected density increase? Scientists have proposed a few possible explanations, though none of them are fully confirmed yet. One leading idea involves the shape and structure of the local interstellar medium itself, the specific patch of space our solar system happens to be passing through right now. Some researchers believe our sun is currently moving through an unusually thin, hot region of interstellar gas, and that Voyager 1 may now be approaching the edge of that region, entering denser material that was always out there, just farther away than anyone initially anticipated. Another possibility involves the heliopause boundary itself, acting almost like a kind of pressure wall, compressing and altering the plasma density in the region immediately surrounding it, an effect that could gradually fade the farther Voyager travels beyond it. There's also ongoing research into interstellar turbulence, essentially small-scale chaotic fluctuations in density and magnetic fields that ripple through the interstellar medium, which could be creating localized pockets of denser plasma that Voyager happens to be passing directly through right now, rather than reflecting some larger galaxy-spanning trend. To be completely clear here, because this is important, none of this involves anything resembling contact, signals, or communication from an outside intelligence. This is not that kind of story, and it's worth saying plainly. What Voyager 1 detected is a natural physical phenomenon, plasma oscillations, the same basic physics behind auroras here on Earth or the solar wind itself, just occurring in a region of space no instrument had ever directly sampled before. The reason this keeps making headlines isn't because it's spooky. It's because it's genuinely unresolved science, real data that doesn't yet fit neatly into our existing models. There's something worth pointing out about the sound itself too, since NASA actually converted this plasma wave data into audible frequencies that humans can listen to. What you hear is not a voice, not a message, and not anything resembling language or intention. It's a faint, eerie, almost musical tone, generated by electrons vibrating at specific frequencies as they interact with the surrounding plasma. Scientists sometimes describe it as the background hum of interstellar space itself, a sound that's technically been playing out there this entire time, completely inaudible, until a 50-year-old spacecraft happened to be in the right place to finally pick it up. Researchers have been careful to separate genuine scientific mystery from online speculation here, and for good reason. Whenever a story like this breaks, a certain corner of the internet immediately jumps to theories involving alien contact or hidden signals. Scientists studying this data have been fairly blunt about that possibility, noting there is currently no evidence whatsoever supporting anything like an artificial or extraterrestrial signal buried in Voyager's readings. What they have found is something arguably more interesting from a scientific standpoint, a real physical anomaly in the density structure of the space surrounding our solar system, one that existing models simply didn't predict. It's worth remembering just how remarkable it is that we're getting this data at all. Voyager 1 is now more than 15 billion miles from Earth, so far away that a radio signal traveling at the speed of light takes over 22 hours just to reach it, and another 22 hours for any response to make its way back to mission control. That means every single command sent to Voyager 1, and every scrap of data it sends home involves a round-trip communication delay of nearly 2 full days. Troubleshooting any issue on a spacecraft. This distance isn't like fixing a glitch on your phone. It's closer to sending a letter into deep space and waiting patiently for a reply that takes the better part of 2 days to arrive. And Voyager 1 is not in great shape these days either. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert the heat from slowly decaying plutonium into usable electricity. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert the heat from slowly decaying plutonium into usable electricity. Unlike solar panels, which become essentially useless this far from the sun, where sunlight is thousands of times weaker than it is on Earth, these generators don't depend on sunlight at all. They work by harnessing the natural heat, released as plutonium-238 steadily decays over time, converting that heat directly into electrical power through a solid-state process with no moving parts to wear out. It's an elegant, remarkably durable design, exactly the kind of engineering choice that made a 5-decade mission even remotely possible in the first place. The power source has been steadily weakening year after year since launch, forcing NASA engineers to make difficult decisions about which instruments to keep running and which ones to power down permanently, just to keep the spacecraft alive a little longer. Multiple instruments have already been shut off over the years, specifically to conserve what little power remains. Every year that passes brings the mission closer to its inevitable end, which makes every new piece of data Voyager sends back feel a little more precious than the last.